All right, hi everyone. Welcome to today's seminar session presented by one of our very own, Dr. Lena Mamykina, Associate Professor of Biomedical Informatics. Today she'll be presenting, Do People Engage Cognitively with AI? Impact of AI Assistance on Incidental Learning. Dr. Mamykina is, as I said, is an Associate Professor in Biomedical Informatics. Her research resides in the areas of informatics, human-computer interaction, ubiquitous and pervasive computing, and computer-supported collaborative work. Her research focuses on the design of innovative interactive systems in health that incorporate machine learning and AI. Prior to joining DBMI as a faculty member, she completed a National Library of Medicine postdoctoral fellowship at the department. And with that, please take it away.
Thank you so much. Hello, everybody. Thank you for joining. I'm going to be talking about something many of you know me and you know my work on technologies for chronic disease self-management, but I've decided to talk about something different. It's related, but a bit outside of what I traditionally do in our department. And not many know of this work, so I am looking forward to the discussion. I specifically made it a bit shorter so that we can have more time for questions and discussion. And today I'm going to be talking about AI and ways individuals engage with AI cognitively and how they think about it and how they reason with it. And the reason why I am talking about AI is because, as we all know, AI has been an integral part of biomedical informatics practically since its very beginning. And from the very beginning of both AI and biomedical informatics, we all know early examples of knowledge-based AI systems that were designed to support clinical decisions and that emerged in the early 70s. One of the better known one is by our own Ed Shortleaf. Importantly, these systems were rarely envisioned as autonomous. If you read those early papers, typically they would say that they never meant to replace clinicians. They were meant to enhance and augment clinical decision-making and were envisioned as a symbiosis between a computing system and a human user. And that's a vision that can be traced back to early days of modern computing and computer science, advocated by Joseph Licklider in the 60s, and probably even earlier by Vannevar Bush in the 40s. Over the years, however, many factors contributed to the decline in AI rhetoric. When I started my PhD program in early 2000, we practically talked about, in a computer science department, talked about AI as historic trends, not something that people still did at that time. And those factors included, among many others, overly optimistic expectations of achieving general intelligence, and also a realization of costs of developing and maintaining very complex knowledge-based systems that needed to reflect evolution of expert knowledge in different fields, including medicine. And perhaps as a result, clinical decision support arguably shifted its focus somewhat from supporting complex medical decisions to providing important but more mundane assistance through reminders and reinforcing adherence to guidelines, as is indicative from this quote here by some of the, again, well-known researchers in clinical decision support. However, new advances in artificial intelligence, and particularly transition of emphasis from knowledge-driven to data-driven methods that use machine learning, somewhat reinvigorated the field of clinical decision support and opened new opportunities to support, again, more complex clinical decisions that were its original target. And perhaps not surprisingly, these new approaches brought new challenges. These models, while incredibly accurate, align poorly with human thinking and reasoning, particularly black box models based on neural networks that are typically inaccessible to human inspection, which present a barrier to the vision of human AI symbiosis. This leads to an increasing dichotomy in the perception of AI as both deterministic in that it relies on computation, but at the same time somewhat magical. It produces behaviors that cannot really be accounted for or explained even by those who created AI systems. And in our class last semester, we read a very interesting paper that sort of called this phenomena Enchanted Determinism, a term coined by Max Weber and used in relation to AI in a paper by Alexander Campolo and Kate Crawford, who argued that property of AI shields its creators from the responsibility of the behavior of AI-driven systems. Perhaps as a consequence of that, there are increasing concerns now that AI-driven systems exacerbate existing inequalities, biases, and disparities. And our own group on justice informatics, I think, is very well familiar with those. So we're all aware of increasing concern and research that tries to address those issues. And in addition to fairness and bias, explainability of AI systems became an area of new research and a new branch of research in AI that specifically focuses on generation of explanations that could accompany AI outputs such as inferences, predictions, and recommendations that can help its human users to leverage their own knowledge, their own skills and experience in critically examining the AI outputs to inform their own decision-making. Again, this goes back to this idea of human-AI symbiosis. This, however, rests on an assumption that human users of AI will indeed engage with explanations if those explanations are made available. And this really brings us to the focus of my talk. This work is a collaboration with Christoph Gaius, who is a professor at the computer science department at Harvard University, and he is leading an intelligent interactive systems group there. We've been collaborating for many years and wrote together on topics of collective intelligence and learning in online communities. And recently we sort of shifted our focus a bit away from collective intelligence among humans and more on AI, artificial intelligence, and its impact on human decisions and actions. And the study I'm going to be talking about today was just a couple of weeks ago actually presented at a conference called Intelligent User Interfaces. And I'm including citation for this paper at the end of my slides. So the questions that we wanted to ask in this study were around this idea of cognitive engagement with AI and the impact of AI on decision-making. Specifically, we wanted to know, do people make better decisions when presented with AI-generated recommendations? What is the impact of explanations on individual decisions? And how do people engage with those explanations? And I'll talk about what we mean by that in a little bit. And as somebody with both Christoph and I have background in computer science and HCI, and we are very interested in the design of interactive systems. And from that perspective, our perhaps most important question was, is there an impact of presentation of AI output, of the design of the AI output on decision-making and engagement that we can take into consideration when designing AI-powered systems that are meant to support human decisions? So this study, like my other studies with Christoph, were conducted in the context of Lab in the Wild. For those of you who don't know, I suggest you check it out. It's an online platform for psychological/social experiments where millions of people around the world can come in and take short game-like surveys that address, again, different factors. You can see some titles here. We've done several studies with this in the past with this platform. One of the advantages of this platform is that you can recruit a large number of people in a very short time frame. The experiments need to be very short and engaging and exciting. and that the individuals or demographic characteristics of people who frequent lab in the wild actually are quite representative of the countries where they come from. So it's a very diverse audience that can be quickly recruited for small experiments. Our task here, and this is where my research in nutrition management comes in, is called nutrition knowledge test, where we ask individuals to look at two meals presented side by side, pictures, obviously, of two meals presented by side by side with a very short title and description of them. And we ask them, which meal has more of a particular macronutrient, including carbohydrate, protein, fat, and fiber. There is a key difference. The meals are very carefully selected and are similar in all respects, except for one key ingredient that makes a substantial difference in that particular macronutrient. So here, for example, we see two green platters with some vegetables and greens. One of them has red beans. Red beans are very rich in carbohydrate, which immediately skews the carbohydrate content towards that meal. So if the question is which meal has more carbohydrate, the correct answer is the one with red beans. That, however, requires nutritional knowledge. Somebody needs to know that the difference between those two meals is red beans, and the red beans are rich in carbohydrate. Now, the way this study is conducted is because we're interested in, I'll talk in a second, in both accuracy and learning as individuals go through this test. It's conducted in three phases. First, we show individuals a bunch of meal comparisons and just ask them to make the choice, one or another. Without any assistance or any feedback. This is our pretest. This is how we test their background knowledge of nutrition. Then they're presented in the second phase with some intervention. Feedback, assistance, I'll talk about that in a little bit. But again, it's some kind of intervention that helps them to make that decision. And that's where we measure the accuracy, again, of their decisions as they receive the intervention. Then in the third phase, we take away whatever support that they had. And again, we ask them to go through a few more meals, making those comparisons without any assistance. And this is our post-test phase, where we measure their learning. Because again, this is where they're no longer receiving any assistance. So whatever improvement they can achieve in accuracy, it should be attributed to what they've learned while they were performing this test. Our intervention. Here we are not doing the actual AI, we're simulating AI that can provide two different things. First, it can provide suggestions for correct answer. For example, we have this intelligent meal assistant that can make a suggestion. The meal assistant thinks that this meal is high in fiber, pointing to the appropriate meal. It can also provide an explanation for the suggestion. That sounds something like this. Reason: corn contains more fiber than many other vegetables, particularly green vegetables like cucumbers. Now, this is what's called a contrasting explanation, where it specifically attributes the difference between two items to a key underlying property and contrasts it with another item that lacks this property. Now, contrasting explanations there's a lot of research in learning sciences on contrasting explanations, and they've been shown very successful in many different areas that require learning. And in our case, again, both suggestions and explanations were generated manually by human experts, by registered dietitians, but we were very specific to keep them in a way feasible, in a way that can potentially be replicated by contemporary AI systems. And in fact, we are already working on some of the systems that can actually do something like this. Now, as I said before, our outcomes here we're interested in are accuracy, in the moment benefit, and we measure it as a change in accuracy between the intervention phase and the pre-test phase. But we're also interested in learning gain, which is the change in accuracy that occurs between post-test and the pre-test. And this is the part that is the key part of this experiment, because this is what shows, what helps us to assess this learning, particularly incidental learning that occurs as a result of engaging with explanations. Again, many AI systems are not really designed to promote learning. They are designed to support decision-making. Our hope is that we can use this incidental learning as evidence of engagement with explanations. So let me show you the examples of what it actually looks like. We have two different baseline conditions that came from our past studies of collective intelligence, where we wanted people to learn from feedback of others. So here you see two meals. An individual makes a choice and then receive a feedback that tells them whether they're correct or not. And that's it. Now, from our past research, we know that this particular condition does not lead to learning. Just receiving correctness feedback without explanations does not lead to learning gains. Now, our second baseline is a little bit better, and this is what we use as a gold standard for learning. This is correctness feedback with explanation. An individual is presented with two meals, they make a choice, and then they receive whether they're correct, the feedback, whether they're correct or not, and an explanation of the nature that I showed you before, the contrasting explanation. So these are our two baselines. Now let me show you our three different AI conditions. One is recommendation plus explanation. So this is your typical way of representing AI output in decision support systems. An AI system makes a recommendation and provides an explanation for this recommendation. For example, here the meal assistant shows which meal it considers to be higher in protein and provides an explanation for why. Now, the second condition here is a little bit trickier. What we wanted to do here, and again, I'll explain all this a little bit in just a couple of slides, but we wanted to introduce a little bit of variation here. And instead of providing a suggestion and explanation right away, we first ask individuals to make their own decision. They look at two meals, they decide which one is higher in fiber. After that, they receive a recommendation from a meal assistant and explanation, and are asked whether they want to update their choice. So they make their own choice, then they receive additional information with a recommendation, and then they can decide whether to stay with their original choice or to change it. And the third condition is where the meal assistant doesn't actually make any recommendation. All it does, it provides an explanation. It's an additional piece of information that has to do with nutritional composition of these two meals. It's the same contrasting explanation that we've seen before, but the arrow is not pointing to any particular meal, and an individual user has to decide for themselves how to use this information to make a decision. Now, let me go through these conditions once again. So the two baselines, one, a minimal assistance, just the correctness feedback. Again, we knew from previous studies that this should not result in learning. The second one is the gold standard, where we knew that correctness feedback and explanation. This is a study conducted by our postdoc a few years ago, Marisa Burgermaster, who showed that that condition actually does result in learning, not only in improved decisions, but also learning. And the three AI conditions, where the first one, your basic vanilla flavor AI decision support system, recommendation accompanied by explanation. The second one is called updated design. So this is a condition, again, where we ask individuals to first make a choice, and then we give them recommendation after that. Now, this condition came out from some of the study conducted in Christoph's lab by, I believe, his either PhD student or postdoc, Jana Buchinka, who explored this idea of cognitive forcing function. And what they found is that when individuals are asked to make their own decision and then provided with some kind of intelligent support, they engage with cognitive support more. And that leads to reduced over-reliance on AI. Now, the third condition here, the explanation only, came or was inspired by some studies conducted in the lab of Keri Karahalos, particularly her students, in the context of driving decisions following guidance from AI system. What they found is that when individuals were presented with explanations, in their context, visual graphical map explanation for driving directions, they actually had a much better memory of the locale and the location of different places than if they simply just followed very minute-to-minute instructions, turn right, turn left, which resulted in better decisions, but no learning of the environment where they were driving. So we thought that this may be an interesting condition to try in our case, again, to encourage deeper cognitive engagement and learning. So these were the conditions. Feel free to jump in if you have questions. If not, I'll just continue. All right, so here are our results. Again, with the lab in the wild, one of the benefits is that you can recruit a considerable number of participants. We had over almost 700 people who participated. And we conducted the studies as 3 separate experiments. Each of them had 2 baselines that I've discussed, and each of them focused on one AI condition. So either explanations with recommendations with explanations, forced cognitive function update design, and the third one is explanation only, but no recommendation. Now I'm going to be presenting results looking at both the accuracy in the moment. I see a raised hand. Lenin, do you have a question?
Hi, yeah, a quick question. I wonder if the AI explanation is always correct, or if the audience, like the people who take this test knows that this is the thing that they're being tested on, like this, they shouldn't really trust the AI, or like what kind of prior belief they should have on this AI?
Excellent question. And I may have had it somewhere on the slide, but I clearly forgot to mention it. So in this particular case, after some debate, we decided to make AI always correct. There was no instruction to the participant as to whether they should always trust AI or not. We left it to their own judgment. However, the assistance was designed to always be correct. And I'll talk about this as one of the big limitations of this study. But we'll get to that in a minute. Does that answer your question?
Yes, thank you.
Okay, great. All right, so this is a brief demographics. There's more in the paper. Basically, it's a relatively even split between male, female. There's a variability of different ages. And generally speaking, participants in Lab in the Wild tend to be technologically savvy and slightly more educated. As you can imagine, these are people who come to research sites hosted by Harvard University. All right, so our first experiment, when we look at recommendation and explanation. So when we look at the immediate benefits of AI assistance, we see, and here again, you see a comparison between 2 baseline, minimal feedback, and explanation and feedback. And the last one is always going to be the AI condition. Here it's recommendation and explanation. we see clearly improvement in accuracy, right? When individuals make their own decisions, they have mixed levels of nutritional literacy. Sometimes they get it right, sometimes they get it wrong. In a condition when they receive recommendations from the AI system that is always correct, they improve their accuracy by a significant amount. However, what we see is there is no learning. When they receive recommendations and explanations at the same time, there is no learning impact, which means that they make more accurate decisions when they have recommendations. But when you take it away, they are no better than they were at the baseline. Here you see that as we expected, our middle condition, our second baseline, which has explanation and feedback, does indeed lead to learning gains. But the AI condition that has explanations does not, which was not exactly what we were hoping for, but I'll talk about what we think is happening here. So our second AI condition is this idea of updated design that forces individuals to first make their own decision and then provides them with AI-generated recommendation and explanation. Here again, we see that when they first make their decision, so this third bar, update, initial, this decision is no better than their baseline, because why would it be? However, when they receive assistance from AI, they actually improve their decision considerably. So again, even in cases when they make their first decision incorrectly, then they receive recommendation and explanation, and they make a more accurate decision as a result of that. However, no learning. That condition, just like the first one, does not result in learning gains. So this is interesting because on one hand, you would think that they're making the decision, they are reviewing recommendation from the AI system. It either agrees with what their original solution or not. In many cases, as you can see, their initial accuracy is actually quite low, and it improves quite a bit, which means that they've changed their mind. But the explanation still didn't have any impact on their ability to make better decisions in the future independently without the AI assistance. So this is worrisome. Now, here's our last condition, the one where it's even, we're going further in the cognitive forcing function. In here, we are giving individuals only the explanation, but no recommendation. They have to make their own decision. Once again, we see a considerable improvement in accuracy as they're receiving this explanation. Remember, there is no suggestion here, and yet the improvement in accuracy is comparable to all the previous AI conditions. And ta-da! Here we finally see an increase in learning or learning gains. And here, this learning gain is comparable to our gold standard, to this middle bar here, where they're receiving correctness feedback with an explanation. So out of our 3 different AI conditions, only this one, the one which displayed explanation but no recommendation, led to both improvement in accuracy in the moment and also learning gain. Now let's think about what does it all mean and what do we do with it going forward. So the good news is that overall, our AI intelligent assistant helped individuals achieve higher accuracy. But again, as this was a great question, Linian. The caveat here is that in this study, AI was always correct. which, as we all know, is not necessarily the case with real-world AI systems that have mixed accuracy, that perform better on some tasks in some cases and worse on others. So to what degree this will stay true in case of this mixed accuracy systems remains an open question. Now, the bad news, or the concerning rather news here, is that we found no learning gains when AI recommendations were accompanied by explanations. Now, the caveat here, and why I wanted to hear Vimla's opinion, who I hope is still in the audience here, is neither Christoph nor I are cognitive psychologists. So we're trying to figure out what some of the cognitive mechanisms behind this effect, or lack of effect rather, are. And something that we came across again is this idea of cognitive engagement. This is a term used a lot in learning sciences. And typically it refers to, I have a quote here from one paper, to a psychological state in which students put in a lot of effort to truly understand the topic, and in which students persist studying over a long period of time. Now, there is a big difference, arguably, between extended period of learning in the classroom and what we're doing in our study, which is this in-the-moment, quick engagement. However, it could very well be that some of the mechanisms are going to be similar. And since most of the people in this audience are students, I'm sure we're all, and I'll use we, are familiar with an effect where you listen to a lecture and then there's a slide and then you're kind of there, and then the person moves on to the next slide, or the lecturer moves on to the next slide, and you have no idea what you just heard. This happens with conference talks also, when your attention drifts away or you're thinking about something else, and it could very well be that you are attending, you are listening to the talk, but not cognitively engaging with it. So this level of engagement doesn't leave lasting impact. It prevents learning from happening over time. And our hypothesis is that this is exactly what's happening when individuals are presented with explanations that come together with recommendations, is that there's a chance that they don't even read them. We didn't look, for example, at eye gaze. There is a way to more explicitly examine this, which we haven't done. However, it is, again, one of the possible explanations for this lack of learning is that individuals are simply not engaging with those explanations. We know, however, that the explanations can be impactful, because in our second baseline condition, these same explanations led to learning. So there is nothing wrong with the quality of explanations. They have the potential, but in this specific case, they do not result in learning. Now, what makes it worrisome is that with all the ongoing research on explainable AI that focuses very specifically on the quality of explanations that can accompany other types of AI output, if our study is correct and we are correct about the cognitive engagement, the quality of explanations is not going to change whether individuals engage with them or not. And it is particularly concerning given increasing evidence that people tend to over-rely on AI in different domains. And the study I'm referencing here, Maya Jacobs, recently looked at over-reliance on AI-generated explanations in the clinical domain. So these trends, or this can happen in many different domains and contexts, including health and medicine. The good news here, however, is that with careful design, we actually can promote learning, and in a way, I don't like the term force, but in a way can enforce this kind of cognitive engagement in our case, by presenting explanations only and forcing individuals to come up with their own conclusion. Now, the trade-off here is this is probably not going to be a panacea. It's not going to be a silver bullet, because the trade-off here is the cognitive burden. As you can imagine, if every time a clinical decision support system was forcing its users to make their own decision, in some cases it is appropriate, but in some cases it could be too costly in terms of cognitive effort involved, and may lead to withdrawal, lack of adoption, workarounds, and other things as individuals try to lower the cognitive burden of engaging with AI systems. I see a message in the chat, but my mouse is not really working, so I can't see what it is.
Question, have you tried looking at the order of when recommendations and explanations are presented, from Amanda?
Well, that's exactly what we're doing here. We are varying the order in which we're presenting recommendations and explanations. In our third condition, we're presenting explanations, but not recommendations. And Vimla has a question.
Hi, Lena, it's
Yes.
Vimla. It's really a very exciting study, and congratulations. This is very important. With laboratory-based studies, such studies are done before you can start putting that into the real field. And you know, some of these things are not new. Explanations and learning go together, which is well known. AI-based explanations, well known. What's really exciting is the conditions under which cognitive engagement happens during explanations, and its recommendation is accuracy and design intervention. I think that's something very new, and I think it's important. This is a short-term study. In other words, the learning over a short period of time. What will be interesting if the learning continues over a long period of time, because it's really, learning is about transfer of information from one situation to another. To how long does it carry through before you have to reimburse it again with new information or new design, or reinforcing constantly do that? That would be really interesting. So the other thing that you raised, which is also important, which is that students are cognitively challenged when they have to generate their own assessment and then look at the explanation. And of course, it's cognitively effortful. But that's what learning is. It's cognitively effortful. So for learning purpose, this is very good, it's excellent. For performance purpose, it's interfering with your performance, because if you want, you can't have constantly learning all the time if an expert is performing, because they only look at their explanations only when it's needed. If they agree with the AI system, then nothing happens. Then they're fine. But if the AI system is wrong, then they need to fall back on that explanation, which really says that AI should have explanations somewhere along the way so that they can fall back on it when they need it in the design, but not to be there all the time that interferes with utility. You know, I think this is very important, and I congratulate you. And
well, thank you so much.
And I look forward to more discussions on this, okay?
Absolutely, absolutely. Vila, you're raising fantastic points. This is all absolutely true. And I think the challenge with design of systems like this is going to be to sort of balance the learning with the and critical sort of inspection and critical interrogation of AI system with additional cognitive burden. Because, you know, if only we knew when the AI system is correct and when it's not, and when there is a need for additional cognitive engagement, which sometimes it is possible, actually. There's a lot of work on indicating uncertainty in, for example, inferences and predictions within AI systems. So one way to go about it is maybe to increase the kind of demand on cognitive attention, or this cognitive forcing function, with increased uncertainty in the inference, and then decrease it as the certainty goes up. But again, even that in itself is sort of a judgment also. So I think there's a lot of interesting design work that can happen, conceptual design, thinking about how to balance the workload with the need for this cognitive inspection of the system.
I think these are all very important questions, and they could be, some of these could be resolved at the laboratory based, to kind of go one factor at a time. Once you go into the real world, you start to see how these factors start to interact with each other, together with the things around it, like the workflow. But I do believe that what you're doing is a great stepping stone, understanding one variable or critical variables one at a time before you go into the major study.
Fantastic. Thank you so much. Before I take more questions, let me quickly, because we seem to be going into discussion, let me just list you, don't think I am aware of the limitations of this study. I'll just quickly go through this because there are quite a few. One is, as we've discussed before, here we are taking this idealistic scenario of AI always being correct, which we know is not the case in the real world scenarios. The second limitation has to do with the nature of the explanations themselves. Now, contrasting explanations are very effective, but generating them computationally is in itself a challenge. There is some work on figuring out how to do that. But at this point, again, our explanations were carefully written by human experts. In the AI world, we will have to rely on explanations that are generated by AI systems themselves. And then the last limitation here, and that one I'm particularly acutely aware of, and perhaps of less concern to Christoph, but definitely is a big concern for my side of this research, is the domain and context. Now, arguably, lab in the wild is a fun place where people come to do fun experiments, but the cost of making a mistake is practically negligible, right? And in this context, it may be very easy for individuals to disengage, to just ignore explanations because it really doesn't matter. One might easily argue, and I might myself argue, that in the context of decisions where the cost of error is much greater, the dynamics might be different. And then people may be much more inclined to cognitively engage with explanations if their decisions actually have consequences, real world consequences. Now, again, the research by Maya Jacobs, what did I just do? Showed that people over-rely on AI, even clinicians, highly trained clinicians still over-rely on AI. So it could be that the findings of our study may translate into a phenomenon that we would observe in the clinical context, but we haven't studied it in the clinical context. And I'm very curious to see how we could structure a similar study, but in the context of medical decisions. So that's pretty much all for the talk. I will share the slides and I'm including all the references here, and we can go into questions. So I see Kong.
Hi, Lena. Very nice talk. Sorry I missed the first part of your presentation, but I guess my question is, if that's related to your first part of the presentation, I apologize for this. So my question is trying to extend the discussion on the cognitive burden and the cognitive engagement itself. I think AI itself is just such a broad word, right? Some of the AIs, I think it doesn't really need an explanation. Sometimes it's not about prediction. It's just like a reminder. And in that case, all of the reason we want this AI probably is to reduce the cognitive burden of the clinician itself, right? So in that case, do you think we still need the cognitive engagement, which is something we want to get rid of them at the first place when we design this kind of AI, right? I agree, some AIs we do need this kind of a cognitive engagement. For example, those predictive models, which for sure you want some explanations from those AIs. But sometimes it's just like a reminder. If you don't call that AI, I'm totally fine with that. That's just my comment here.
So I think it's a very interesting question, and we kind of going between the clinical decision support, the AI, where does it all fit? But this is what I was talking about, that some clinical decisions may not really require this engagement. Because if it's about reminder, for example, it's questionable whether or not you need AI for this. A lot of clinical decision support are based on simple guidelines and rules. And in this case, it's less of a concern whether clinicians actually are engaging with them or not, because you can be almost certain that those are correct. If this is a reminder to talk to a patient about flu vaccine or something like that, or do an eye check for somebody with diabetes, those are non-controversial and there is really no need for engagement. However, if more complex AI system is making a diagnostic recommendation or showing a risk factor that may require invasive procedures for confirming or changing treatment, this is where I think, generally speaking, we all as a community, as a research community, hope that clinicians can actually use their own judgment and can be assisted by AI systems, but they still need to be engaged because the decisions will still reside on them, and those are not non-controversial decisions. This is where some of these sort of questions will come in, is are those really two, how clearly can we distinguish between those two? Is it a spectrum? And how do you decide where do you lean towards one side of it, where it's just a quick engagement, quick support, no need to think about it, moving on, versus wait, no, let's pause a little bit and think about, is that the right thing to do or not? My guess is that it's not a binary, it's a continuum, and somehow we need to figure out which side of this continuum we're going to be basing our sort of assistance on. Tara.
Thank you.
Sure.
Hi, Lena. Thank you for the talk. This is really interesting. I'm curious about like this assessment. There's this hypothesis of lack of cognitive engagement when the recommendations are presented. Have you thought about ways, or like, are there standard ways of assessing cognitive engagement just generally? Like, I'm thinking about this assumption that the AI answers are always right, but if we look at the ones that are wrong, for example, can we see, and like people can put an answer and then change the answer in response to the recommendation. Maybe like with a recommendation, they're always blindly following what the AI is saying versus an explanation. Sometimes they just agree with the AI. Are there ways like that to kind of assess cognitive engagement that have been looked at?
Right, so great question. We talk more about this in the paper. I kind of skipped that part here. Unfortunately, no. Well, so yes and no. There are more formal ways to assess cognitive engagement. However, they were designed in learning sciences in the context of education. They really are meant to assess cognitive engagement over a longer period of time. And they're measured in, for example, how many hours the student is spending doing homework. Not the cognitive engagement of how deeply they are processing information that they're receiving right now. Now, what we're trying to do now actually is to find a way to use brain imaging to get at that in the moment. Because our suspicion, again, is that if we're dealing with different cognitive processes, there should be a corresponding difference in some physiological signal that we may be able to capture. Vimla is raising her hand. I think she has something to say about that. Am I correct?
Actually, I didn't. Continue, please. I have another question.
Oh, I see. So right now, we don't have a way of measuring more precisely this in the moment cognitive engagement, but I'm talking to our colleagues in our psychology department to see if we can more explicitly look at brain activity to capture something like that. So that could be a fun project to do. Sorry, Vimla, you have another question then?
Yeah, I was going to have a kind of a suggestion in a way as well. The task that you selected, looking at the nutrition task and the pictures, be careful of, if you're going to use that for other cultures, making sure that the people who don't eat pork and meat, they're not in there to be cultural bias, make sure those don't get in, you know, those kinds of tasks. And to be culturally sensitive to what kind of food they select. But more importantly, you're looking at people's perception because they're seeing something in front of them. You're seeing a picture of food and automatically you see something green and something, there are beans that are brown. You have a certain assumptions made on the perception. So there is a sensory perception. So you got to be careful whether you're measuring cognitive or not sometime, because there's a sensory perception and there is a cognitive perception, a little bit deeper than just sensory, you know. And then there is the cognitive engagement. So it's got to be a little challenging. Otherwise, you just measure what they see in front of them and assume based on that. And if the AI system is wrong, then you tend to get into more difficulties. So making sure that it's a more challenging task, that you're not just measuring the sensory perception, but measuring the cognitive perception is another level and much deeper engagement after that. Just a selection of tasks. I don't know anything about much more than what you have selected there and how it affects it. But these are the considerations we usually make when we select tasks, you know, and especially analogical tasks for pre-post, you know.
Absolutely, all great point, definitely. And I think, generally speaking, I would really love to conduct this task or this study, some version of the study, when participants are coming in person, because there's only that much we can do in a study that's conducted, you know, online, where participants may be wherever. They may be accessing it on their phones or on their computers. We have no control over anything, really.
Absolutely.
So it gives us a lot of numbers, but it doesn't give us much control over how they're exposed to it, how much time they spend on it, and why. So I think there would be nice to complement it with a more controlled settings.
Absolutely. Thank you.
Thank you. Adrienne.
Yeah, hi Lena, thanks so much for that awesome talk. You're really contributing to an important gap that we keep identifying. So it's very awesome that you are working on it. And a lot of the questions that I had you addressed in the discussion and the limitations, and especially around like the context, the medical context, the cultural context. And like I'm wondering about how like the cultural context can be addressed in AI generated explanations, and worried about disparities that exist being exacerbated by, you know, explanations that are maybe relevant to more relevant to somebody's one culture and not relevant to somebody else's, or, you know, would have a different explanation or things like that. And I wonder if there's like ways to address that. I also just wanted to mention that I agree. I think that the difference in motivation and the folks who might have engaged in the first experiments might be different in a meaningful way when you do this with like the folks that, you know, in person and things like that. And so I was wondering if you'd thought about ways to kind of tailor the recommendations for the background of the participants to avoid, you know, exacerbating disparities.
So this is a great question. One thing I do want to point out that this research was not about how to generate explanations, right? So this is a whole other area of research in AI. And what we specifically focused on is, if you have explanations, how do we manipulate or not manipulate the presentation of those explanations so that people actually read them and engage with them and understand something from them? But it doesn't take away from the need to generate quality explanations And I mean, cultural backgrounds is definitely one area of it, but there's also the education and the level of literacy. The way we wrote our explanations was meant to be for a relatively low levels of literacy and nutritional literacy. And nonetheless, they still required some knowledge of nutrition. So I'm fairly certain that even our sort of simple explanations probably excluded some individuals or were inaccessible to some individuals. So I don't have simple answers to your question, except that these are good questions to ask as we're working in this area. And as we sort of think about ways to incorporate explanations, these are all very good ideas to, or rather good questions to be asking. A somewhat different approach to this, if you also want to open it in a different direction, is explanation is not the only way to make systems explainable. Right here also, we specifically focus, because this is kind of where the research community is going, we specifically focused on explanations that are added to a black box system. But as you probably all know, my own research with Lauren and with George and with Dave goes more into creating systems that don't require explanations. And that could be open, sort of open box models. But even there, I'm fairly certain that questions of education, knowledge are going to be also very important. And how do we design those systems that don't exclude populations that we would like to include? I think Craig is reminding us that, oh no, but we are almost out of time. So maybe another, if there are any short questions, I'm happy to take. Oh, Hanjin, sorry, I just noticed.
Oh, no problem. Thank you for the very nice talk, and Lena. I just, well, I look at your title, Do People Engage Cognitively with AI? Then I was wondering the takeaway message, is that true, that just to confirm that the answer yes or no depends on how the AI is designed and presented to the user?
That's what our study showed, yes.
Yes, and then the next question I was thinking was then looks like this question, the answer to the question really depends on each individual application. Like in here, this is about nutrition, right? And you tell this is better than that one, that is better than this one, right? But in different application, looks like it has to be designed individually according to different applications. Am I right?
Well, yes and no, perhaps. I'm sure as in every design, there are going to be some common patterns for different types of problems and contexts and different design solutions that are appropriate. Like in HCI community, while user-centered design is always the right approach, there are design patterns that have been established over the years where we know what kinds of solutions work for particular types of problems. We don't have to design a completely unique solution for every problem and every situation. But I do believe that we are missing design patterns for AI-driven systems. We're just not there yet. But I hope that this study, and as we sort of continue gaining experience in designing these kinds of systems, we start identifying patterns of solutions that work in different, more sort of high-level general classes of problems.
Thanks.
Thank you all. You are a great audience. It was great to hear all the questions. Thank you for the discussion.